Okay guys, let's take a look at today's lesson. Let's review a little bit about what we've done in this unit. That first lesson we looked at basically three-dimensional vectors. How is that different from a two-dimensional vector? We just kind of talked about that, did some graphing of three-dimensional vectors. The second lesson we looked at projections. We learned that vectors don't have to be, stuck on with respect to the x, y, and z axis. They can actually be anywhere, and you can project one vector on another regardless of where it is. So we learned that. Today what we're going to learn is how to do cross products. So cross products are a pretty big thing for us in multivariable calculus. We use them for a lot of different things. Today we're just going to investigate just two things that we would use cross products for. We're going to remind ourselves or learn how to generate them. We're going to generate cross products and then learn what we can do with them. So the first concept I'd like to talk about is, so if you take a look at this, we see two vectors right here, A and B. If we cross these two vectors right here, we get a third vector, and this third vector is perpendicular to the other two. That's a very important concept for us to know, that if I basically cross two vectors, I'm going to get a third vector which is perpendicular to both of the others. So think about it, we're in 3 space, right? We think of these two vectors as being on the plane. The third vector would come out of the plane, and it would be perpendicular to both of the two vectors, both A and B. So that's the first concept, is we are able to find a vector which is perpendicular to the other two vectors. That's one use of cross products. The other use of cross products is a geometric concept. If we take the magnitude of the cross product, we basically get the area of this parallelogram. Kind of envision with me, so I have two vectors and they're tail to tail. If I were to extend these vectors out, it would make a parallelogram. I hope that we can see that, right? We would kind of extend them out. We'd make a parallelogram. What the magnitude of that vector calculates for us, the cross product, is the area of the parallelogram. So that's a geometric use of cross products, is it will actually find the area of a parallelogram that is created by two vectors. If we wanted the area of the triangle that is created by these two vectors, we would basically find the magnitude of the cross product and then half it. The triangle would just be half the area of a parallelogram. And that's really the two kind of things we're going to be talking about. We're going to learn how to do a cross product, and those are the two applications we're going to look at. So let's look at this little device right here. Perhaps you remember from Algebra 2, perhaps you don't, matrices and determinants. So this is a determinant, this U cross V. And this is how we set up our cross product. So in the top row, it would just be the vectors I, J, and K. And then underneath them, you would write the vector components of vector U in order and the vector components of vector V in order. And that's how we're going to set up the 3x3. Again, from Algebra 2, you're probably thinking, when are we ever going to use this? Yes, it is a really big deal. Cross products and determinants are a really big deal. We use them so much in multivariable calculus that students are able to kind of do them in their head. We use them so much because we use them over and over and over again for different kinds of things. So let's remind ourselves, or we'll hopefully just remind ourselves, how do we expand a 3x3 determinant? This is the formula for expanding a 3x3 determinant. We would, for this first piece, we would kind of ignore this column and this column, and these would be written here with the I as a multiplier. The second, we're expanding these. The second piece of it is always subtracted. That's always a subtraction. So we go back to our original one right here. And so now to get the middle one, I'm going to ignore those columns and I'm going to copy down these, right here. U1, U3, V1, V3. That gives me my second one. Hopefully this is ringing a bell because you would have done this last year, I'm hoping. Then the last one, we would basically ignore that row and that column, and we would get U1, U2, V1, V2, again multiplied by K. And we're going to do a few examples of this, so that'll hopefully jog your memory if this is not making any sense. But that's the process that we're going to use to actually find cross products. So we're going to practice that technique. All right, any questions on just the overview? Okay, let's go to the second slide. We have a couple of examples to work. The first example is basically just asking us to find a cross product. So we're just going to practice that technique. How do we find a cross product? We're going to find A cross B. Okay, so the first thing that I'm going to do is I'm going to write it in that 3 by 3 notation. Okay, so A cross B is going to be equal to, so I have I, J, and K along the top. And then I'm going to copy the coefficients of A down. So that would be 3, 5, and 7. Then I copy the coefficients of B down, which is 11, 2, and 13. So that's the 3 by 3 that I'm going to have to expand. Okay, we all okay writing the 3 by 3? All right, so we get that written. So now let's expand it. We have to expand it into 3 2 by 2s. So the first one, I'm going to kind of ignore this column, and I'm going to ignore this column, and I'm going to write 5, 2, 7, 13, and that's multiplied by I. Does everybody see where I got the 5, 2, and the 7, and the 13? Okay, then I subtract the second one. It's always, that's the only one that's subtracted is the second 2 by 2. So now I'm going to ignore this J column, and I'm going to ignore the top row, and I'm going to copy down the remainder. So that would be 3, 11, 7, and 13, and that's multiplied by J. Okay, that's a terrible J, but that is a J. Okay. Plus the last 2 by 2, I'm going to ignore this last column, the K column, and the top. And so I copy down 3, 11, 5, and 2, and that's multiplied by K. Okay, are we okay with the expansion of the 3 by 3 into 3 2 by 2s? Okay, so now if you remember how to find the determinant, we would multiply this cross from left to right, 5 times 13. We would multiply that together. When we multiply 5 times 13, we get 65. And then we subtract the multiplication of the other cross. We subtract the multiplication of the 2 times 7, which is 14. And that's how we find the 2 by 2 determinants, if you remember. So from left to right, that cross comes first. Then we subtract the cross from right to left. Okay? All right. So let's go again. So I'm going to do this cross first, and let's just not say the right to left, left to right. That's kind of confusing. Let's just say this first cross, 3 times 13. 3 times 13 is 39, minus 11 times 7 is 77. And that's J, plus our last 2 by 2. We're going to multiply the 3 times 2 and get 6, minus 11 times 5, which gives us 55. So there's our multiplication. Okay, the last thing that we're going to do is just clean that all up. Do the addition and subtraction that we are asked to do. So 65 minus 14 is 51, minus 39 minus 77 is a negative 38, plus 6 minus 55 is a negative 49. And now I just need to kind of clean it up, make it look really good. Okay? Okay, there we go. That was exciting. So let's kind of clean that up a little bit. So we have 51i plus 38j minus 49k. Now what we've just done is we've found a vector that is perpendicular to both of these vectors. Which you're like, okay, so that's a really big deal. That's great, right? We found a perpendicular vector that is perpendicular to both of these vectors. So that's what one use of the cross product is. Okay, and that's our answer. All right, so let's take a look at the second problem. The second problem is an application of a cross product. What it wants us to do is to find the area of the triangle with vertices at those points, P1, P2, and P3. And so let's think about that for a second. We just talked about we could use a cross product to find the area of a parallelogram, right, that was created by two vectors. What would we do if we wanted the triangle? We would just divide by 2, right? We would find the magnitude of our cross product and divide by 2. That's what we're going to be working on. Now, it's a little bit more difficult because they didn't give us the vectors. They gave us 3 points. So we're going to have to write the vectors. It's important when we write the vectors that we write them so that they connect tail to tail. Right? We want them to connect tail to tail. And so what I do sometimes I will graph those points in 3D. Sometimes I will. In this particular case, you know, or sometimes I don't. It just kind of depends. This is the way that I set the vectors up, or the points. I set the points up to get these vectors. So this is point 2, which is negative 3, 2, 7. This one is point 1, which is negative 5, 5, and 5. And this is point 3, which is 1, 12, and 6. Okay, so when I write these two vectors, I've got to write them. I'm going to write them like this. I'm going to go P1 to P2. I'm going to write that vector. And then I'm going to write the vector P1 to P3. So I need to write them in that order so that they are tail to tail. So vector P1 to P2. So we do like we always do with 2 points. Write a vector, right? Negative 3 minus a minus 5. That gives us a 2. And then 2 minus 5, negative 3. And then 7 minus 5 is a 2. So our vector P1, P2 is 2, negative 3, 2. Okay, so the second vector that we need to write is P1, P3. So the vector P1, P3 we'll go 1 minus a minus 5, which is 6. And then we would do 12 minus 5, which is 7. And then we would do 6 minus 5, which is 1. So now we have our 2 vectors. So we have a few additional steps when we're in context like this. So they don't just hand us the vector. We need to write them. And now we're going to cross them. When we cross these 2 vectors, basically what we're doing is we are finding the area of this parallelogram. Okay, that's what we're finding the area of when I take the magnitude of the crossed vectors. Okay, so let's cross the vectors and then let's do the magnitude of them. So P1, P2 crossed with P1, P3. Okay, so let's cross those. So we have I, J, and K. So let's write down the components of P1, P2. So that would be 2, negative 3, 2, and 6, 7, 1. All right, so let's split that into 3 2x2s. Okay, are we getting a bit more comfortable with this, I'm hoping? So let's go ahead and split that up. So that gives us negative 3, 7, 2, 1, I minus 2, 6, 2, 1, J plus 2, 6, negative 3, 7, K. Okay. Is everybody okay with that? Now we're going to do our multiplication, right? We do negative 3 times 1 gives us negative 3 minus 7 times 4 is, 7 times 2 is 14. I minus 2 times 1 is 2, minus 6 times 2 is 12j, plus 2 times 7 is 14, minus a minus 18. So we're adding that, right? So plus 18k. So let's clean that up and get that vector. So that vector is negative 17i, and then it is plus 10j, then it's plus 32k. All right, is everybody okay? Now we do the cross product. So what we're doing is we need to do half, we did the cross product, sorry. We're going to do half of the magnitude of P1, P2 cross P1, P3 is what's going to give us that area of the triangle, right? That's what's going to give that to us. So basically we're going to do 1/2 square root of, and that would be 17 squared plus 10 squared plus 32 squared, which gives us 1/2 of the square root of 1413. And that's an exact number, and I love exact numbers, but if somebody asks you for the area of something and you tell them that it's half of square root of 1413, they're going to look at you like, what? What is that? So you probably should put it in context, maybe. You can leave it like that. I'm fine with you leaving it like that. That's an exact answer. But if we put it in context, go ahead and do 1/2 times the square root of 1413. We get 18.795. And we want to round to the thousandths because that's just kind of what we do. Okay, are we okay with that? All right, great.